Hello everyone, and today we'll talk about a single phase inverter with a controller. Just we will build on the previous experience that we have. Okay, so first of all we will build an inverter, okay, similar to what we have before, and then after that we'll instead of generating the pulse width modulated signal from an open loop like comparison between the sine wave and the triangular wave, we'll take the feedback from the output voltage or the current if you want, but now we'll focus only on the output voltage and supply the input, okay, supply the signals. And from the information that we have, you will find that we will be able to generate a pulse width modulated signal using a PI controller, okay. And then after that, we'll try to connect a boost converter with our inverter and see how things are going. Okay. So first of all, I'll start with building the inverter. Things is not difficult. I'll build the inverter similar to what we have before, just a bipolar inverter. Okay. Okay. So first of all, I'll try to connect the inverter from the beginning to make it easier for you. I'll not copy from the last time because I know that last time if you copy it, yes, it's faster for me, but it's more difficult for you. But I'll start again from the beginning. So we'll go to the components here and try to add some switches. I'll go for the power semiconductors. Again, because it's an inverter, we need an IGBT with a diode. Okay, so here I will add 4 switches. Okay, connect them to an input power source. So here we'll connect the inverter, and we'll connect this inverter to a DC power source. So we'll go here to sources and add a voltage source. Okay, and then we'll add a load here between the 2 legs, this leg number A and B, let's say. And last time we added an inductor. We didn't add an inductor. We just put this on the load. So I'll duplicate the same thing. Then we'll see the difference if we add a filter for the inverter. Okay, so here we can go to passive components. We need a resistor, we need an inductor, okay. What we will do, we'll connect the output load, okay. RL load here. Last time we said this is how much? Maybe 10 millihenry. It's a big because it's a load, not a filter, so we are not supposed to use this value for a filter. And for this, let's say I don't know, 10 ohms or something. Now again, I'll use the same pulse width modulated signal that we used it last time. Here we said that we have a triangular wave with a sine wave, right? The triangular wave is from -1 to 1, and I will say this the switching frequency here is 5 kilohertz, okay? And the sine wave is 0.9, and the amplitude is 0.9, which means the modulation index is 0.9 as well, with 50 hertz, because we need the output of the inverter to be 50 hertz sine wave, okay. And then we compare these two signals. If the triangular wave is larger or greater than the sine wave, then we have 1. If not, we have 0. We will send these 2 signals to the switches. So switch A will go to switch number 1 and 4, for example, and switch B will go to the switch number 2 and 3. Okay, we go here for the signals. I think we need to go. Okay, we'll select signal from. I'll take it. I'll say this is signal A. We'll put it here for this switch and this. And again, we'll take this one and make signal B. One is here. And the other one will be in this switch. Okay, now the inverter is ready because we have the signals. Okay, we have our bridge, we have the load. We just need to put a scope to see the output waveform. So easy way, just write the name of the, and also we need a meter, voltmeter here, and a meter. And the voltmeter should be here. Okay. What else? We need a multiplexer, isn't it? So okay. So here we put the ammeter and the voltmeter, and then run and see the output waveform. Okay. Now we expect that we have no filter now. Okay, because the output of the inverter just connected directly to the load without any filter. Okay, so we expect that the output of the inverter is just plus minus VDC, right? Here I'll put this one to 400, for example, and start the simulation. We have a problem here. This is not connected. Okay. No problems. Okay, so let's have a look at the output waveform. Do we get the same thing as before? Well, because this 5 kilohertz, so it's difficult to see the difference. So I'll make it 1 kilohertz first and see the output. Okay, so we can easily see the output waveform here. Okay, let's change the parameters here to, let's say, 0.1. Okay, that's fine. Look at, we have the sine wave on the output. The current is a sine wave because we have an RL load, but the voltage is just a chopped pulse width modulated waveform, and the voltage from minus 400 to 400. Okay, now this is an open loop system without any filter. Okay, what I need to do now, I'll add a simple filter, okay, between the input and between the inverter and the load. Okay, so we can add an L filter, okay, and put it here. Okay, I'll remove this from here. I'll make it just R load. Okay, and I'll say that this is a 1 millihenry only. Now, if you want to connect the inverter to a grid, so I think just L filter is enough because the grid capacitance is large, and you are not going to change the grid voltage. Okay, but if you have a standalone system, like a standalone load, so you need to add a proper filter like LC filter or LCL filter. Okay, So what I'll do here, you can see the difference. We have 1 milliampere, 1 millihenry inductance. You can see the difference now. The voltage looks like a bit similar to a sine wave, okay? So it's not a chopped PWM anymore, but this filter is a poor filter, honestly. You can add a capacitor at this point. So we can go here and add passive element. We can add a capacitor. And this is an LC filter. And we know that LC filter is a low pass filter, right? Low pass filter means it will remove the high frequency component, okay? Like the third harmonic, fifth harmonic, and all components, they will be removed, and it will keep the first fundamental frequency, okay? Oh, now looks like much better, right? You can see the sine wave, like the output voltage is very close to a sine wave, but still we have like a good amount of harmonics. So we have two options at this moment. We can either increase the value of the filter, like increase the inductance, increase the capacitance. Let's double check the capacitance. We didn't pick any value. So 100 micro or 220 micro should be fine. So I'll change this one to 220. Okay. So now the sine wave even much better. The output waveform is much better, but also we still have some harmonics, as you can see. What we can do actually, we can also either improve the filter, like increase some of the values of the components, like increase the inductance, the capacitance, or we can increase the switching frequency. Okay, so we can go here, and instead of 1 kilohertz, I'll say it's 2 kilohertz, for example. Okay, and then simulate again and see the, oh, that is very nice. Okay, that is perfect. Okay, if you want, you can even increase the switching frequency more, or add maybe LCL filter. Okay, let's go here and change this one to LCL filter. So instead of LC filter only, we'll add another L here. Okay, so this is what we call LCL filter. Okay, why do we need the LCL filter? If you want your inverter to work as a current source inverter, like to be connected to a grid or to be connected to a load that is a voltage source load or something, like you need an inductor at the terminal. Okay, so LCL filter will be perfect or a very good solution if you want to connect your inverter to a grid, to supply a grid, or to collaborate with another inverter to supply a grid. Okay, in the case of parallel inverters or something. Okay, if you have only one inverter, for example, and you want to supply only one load, so LC filter should be fine. Okay, but in this case, LCL filter, I think it's a perfect solution. We can use it, and then simulate again. You'll find that you have a sine wave with a sine wave voltage with a sine wave current without any problem. Okay. Of course, they are in phase because the output load is a resistive load. Okay, you can add inductive load if you want. And see if this can make any difference. Yes, we have some delay for the current and some distortion here, because the whole component of the inductance being changed. Okay, so when you design your inverter, also you need to take into consideration the load, like the maximum current that you are consuming, if your load is inductive load or resistive load. Most of the time you'll find the load is inductive load. Okay, but for simulation at the beginning, you must be able to make sure that your inverter is working at like the basic requirements for resistive load, without any problem, without a controller. If it works without a controller, then you can move on and design your controller. Okay, so that's why what we need to do now is just design similar inverter to what we have done before, and then I'll use just a resistive load, okay, with adding only filter, okay, LCL filter with the values of like 1 millihenry for the inductors and 220 microfarads for the capacitors, okay, for the capacitor, for the filter capacitor. Okay, now what improvement we need to add for this inverter? Instead of taking a sine wave and compare it with a triangular wave here, okay, this is an open loop system, so we don't take any information from our inverter. What we need to do actually is to take a feedback from the output voltage, okay, from here we take a feedback, and then compare this feedback with our sine wave, with the perfect sine wave that we are sure it's a sine wave, okay. Then we will generate what we call an error signal, okay. This error signal will go to a PI controller, okay. You can use PID controller if you want, not necessary, because PID controller will be more complicated to design, and also the derivative part of the controller will be very sensitive to the load disturbances. So what we need to do is just use a PI controller, or a P controller sometimes is enough. We'll use PI controller for two reasons. The P part, the KP, okay, the P controller part will help to increase the what we call the amplitude, okay, the gain, will increase the gain, okay. So this is part number one. The integration part will help to reach to the stability faster, and these two requirements are enough for our PI controller, for our inverter, no problems. So what I need to do now is to take a feedback from the output, from the voltage. So here I'll take a signal from here, I'll call it V out, okay, V out. We'll take V out from the output voltage here, from the voltmeter on the load, okay, and then take it, compare it with the sine wave here, and then send it to a controller, okay. So what we need to do actually is take this sine wave as a reference signal, okay, take this is from V out, bring a comparator plus minus. So here we can take from mathematical, okay, so we need this one, we need again as well, okay, because if you remember, the output voltage here is how much? It's something in 400 something, okay. So 400 volt, we cannot compare the 400 volt with the sine wave plus minus 1, right? So we need to divide this by a value of 400, for example, okay. So I'll say this is plus minus, and then we'll divide this by, let's say 250 now, and see the output, how things are going. So I'll compare these two. Okay, now the output of this is an error signal. This error signal should go to a controller, to a PI controller, as we said. Okay, you can search for a PI controller from here. You can say a PI, you can select a discrete PID controller, or you can build your own controller like gain plus integrator. It's up to you. This one is like simple to take and use. I'll select PI controller, okay, and then I'll select the values like 1 and 1 or 0.5 and 0.5, for example, for the KP and KI. And also go here and check the discrete time settings. You'll find that the sample time here is very large, 1 millisecond. So I'll make it 1e-5, for example. So to give more accurate output. Okay. What else we need to add? Another gain. I'll add another gain here. So this gain will multiply the error signal with a value like 0.5 or 2 or whatever before going to the controller. You can remove this one, but if you want, for example, to take another loop, like to take the input side, you can add this loop at this point, for example, to make like more flexibility for your controller. So I'll say this is 0.5. Okay. The gain PI is 0.5 and 0.5 here, and then I'll send this error signal, or this is the control signal that is coming out of the PI controller. I will compare it with a triangular wave. Okay. So now we'll take this one. And compare it with the triangular wave. Now we have a comparison between the triangular wave and the control signal. Now we expect that this control signal should be sine wave, okay? But this sine wave is like changeable, modified, okay? It's not straight all the time, okay? Because it depends on the value of the output voltage, okay? So that's what we need. What else we need? I think that is fine, everything. Let's try to simulate and see the results. Okay, you can see here the output is changed. Okay, to examine the performance of our controller, we need to change the load. Like we need to add another load at some point to see how the voltage acts when we have a variable load. Okay, but before going to this, we need to check something here. I need to check the triangular wave and the control signal. Okay, this is very, very important here. If the sine wave, the control signal, and the triangular wave are within the range, that is fine, no problems. Sometimes you will find that your control signal is larger than the triangular wave. This makes a problem, okay? Or you might have over modulation, or maybe you might have unstable system, okay? So we need to make sure that our sine wave is always smaller than the triangular wave, okay? And that is fine here. That is fine because the comparison is fair comparison, no problems. Let's check again here the output waveform that is coming from the output voltage and compared to the sine wave. You'll find that this waveform is okay. I need to simulate again. Okay, so this is the waveform. The output 0.6 is compared with the sine. This point, the maximum is almost 0.6, and this is compared with a sine wave, a perfect sine wave with a 0.9. So this will generate the error signal, and this error signal is going to the PI controller, and then compared again with the triangular wave. Okay. Just I'll remove the names. It appears here. Okay, what else we need to do? Okay, that is fine, no problems. Let's double check the value here. It's 2000 hertz, 2 kilohertz. I'll make it 5. and see the output, you can look at the output here. You'll find that the output sine wave is just a perfect sine wave without any problem. Okay. What else we need to do actually? We need to duplicate this load, and then we have to add another load at a certain point of time. So here I'll duplicate the load, and I will add what we call a switch. It's just an ideal switch to connect this load at, let's say, at half the time, at 0.5 for example. So I'll go here, I'll add this, not this switch, I'll go here and add this switch. Okay, I'll connect it at this load, and at certain point, let's say we need to add a step function here. Let's say, for example, at 0.5. Okay. Okay, so what will happen now? Okay, now we have this load is connected all the time. Okay, and this load is how much? Is 10 ohms. Okay, let's say it's 50 ohms. Okay, no problems. And this one also, let's say this is 20 ohms. Okay, so now what will happen? Now at 0.5, this load will be connected. So the total load will be smaller than the smallest resistance, right? So this is 50 ohms. Then once we connect this load, it will be less than 20 ohms. Okay, this means the current will be increased, and we expect that we have a voltage drop on the output voltage. Okay, now we'll see how this controller will deal with this problem. Okay, now we'll go and make simulation again. Okay, now this is a very small time. Again, we'll increase this one to 1 second. I prefer to make it clear. I'll put the scope into, like, I'll put the voltage and the current in different scopes to show us how the change of the current and the change of the voltage. So look at here, the scope parameters. I'll make it 2. Okay, run again and see. Now you can have a look at the current and the voltage. It's clear that now the current increases at 0.5, but the voltage it's almost fixed, right? You can find the voltage is like straight without any problem, and the current is changed. Okay, and that's why, because we have a controller at this point. It's a closed loop system. Okay, what else you can do actually? Okay, after that we'll connect a boost converter from the input, and by this way we have almost a complete system, a single phase inverter. Okay, now there are many ways to make a controller for a single phase inverter. You can, instead of taking the output voltage from here, okay, you can take the current waveform. Okay, if you want to build a grid connected inverter, you can take the current, for example, or you can take the voltage waveform and measure the amplitude. If you want to control with amplitude, then you can compare the amplitude with not a sine wave, with a straight line with a reference waveform, with a reference signal. Okay, let's say the amplitude that is required here on the output is 400, for example, or 150. Okay, the maximum value is 200, for example. So you can take this 200 from here and compare it with the desired signal, which is not a perfect sine wave, is a perfect amplitude, like 200 straight line. Okay, then you'll get another error signal here. This error signal will go to a PI controller again, and on the output of this PI controller, you'll get an error signal, the control signal. This control signal will be compared with a triangular wave and will be sent to the inverter again. Okay, the key point is we need to make sure that we have a sine wave here. Okay, the control signal must be a small sine wave in order to be compared with the triangular wave. No matter the way that you use, there must be a triangular wave compared with a sine wave. This sine wave must be changeable, and you need to get something like this. The triangular wave, this is the green waveform, okay, should be compared with a sine wave. Okay, sometimes you'll find that the amplitude of this sine wave is changing, so maybe you need to reverse the operator here to make a compensation on the output. But here in our case, we should have no problems. Okay, the sine wave is working well without any problem. So here we obtained almost same results. Okay, but look at this value is very small in this case because we just change the way of modulation. So we send the opposite signal, so I'll keep it this way. So now we have the output without any problem. Now what we need to do, actually, we need to add another stage for this converter, for this inverter, and instead of taking the input from the DC power supply, we can take the input from a boost converter. Okay, like just imagine that we have a PV panel here, and this PV panel or this PV array is giving a waveform, giving a power to a boost converter, and then this boost converter is sending the results to, well, sending the output voltage to the inverter. Okay, so we can build a boost converter now and connect it to this inverter. Okay, so what we need to do is just take a boost converter, very simple. We can connect inductor here at the input, switch, and then we have a diode. We didn't use that before, so we write diode here. Okay, and then we have a capacitor. So simply this is a boost converter. Let's increase the value for this one to be, for example, 500, and this to be 3 millihenries. We need to add a pulse width modulated signal here, or just a square, what we call the pulse generator. Okay, pulse generator. In this case, the boost converter working as an open loop system. Okay, again, if you want to make sure that your converter is working well, you need to make sure, you need to decide this pulse generator just should be taken from the output of the boost converter, or if you want to track, for example, the maximum power point, will you change this one according to the input voltage or the output voltage? It's up to you. So here I'll put the frequency to 1 kilohertz and digital 0.5. It should be fine. Let's check what we got. We have some problems. We need to check the voltage here on the input of the inverter. Okay, you can simply say that the input voltage is very large compared to the previous one. And then we have two options now. Either you need to change the controller, or for example, you want to make sure that your input is 400 volt. Okay, what you can do is just change the value of the duty cycle here. So if you said like 0.5, no, it's 1 over 0.5, so it's 2. Okay, 1 over 1 minus 0.2, that should be fine. I think this is the simplest value that we can use, the smallest value that we can use, otherwise it will be very small. Okay, look at the input voltage here, the boost voltage. Now the boost voltage will be changing as well from 700 to 600, because this, like, everything is connected to each other. Like when we change the output voltage here, the output current, the load is changing, this will make effect on the input as well. So we'll have voltage drop on this side. Okay, so in order to make sure that our controller is working well, okay, as we said before, look at here. So here the current is changing, the voltage is changing as well. So what we need to do, actually, we need to play on this gain. Okay, we add another loop, and this loop must be taken from the input voltage. Okay, once the input voltage is changing, this should send a signal, or in like order, to the controller to make some changes. Okay,